complex functions. One way that a complex function can be described is as u plus iv. Okay, so complex numbers have real and imaginary parts. Complex functions also have real and imaginary parts like this. Okay, so f is differentiable if and only if, well, there's a few other kind of weird situations, but let's not worry about that, where this actually doesn't happen. If and only if the Koshirimo equations hold. If and only if both of these are true. Differentiable at a particular point, okay? Okay, yeah, so that's where the Koshirimo equations come into play. So for you guys, if you have a complex function, you can split it up into the real and imaginary parts, and then you can take partial derivatives of the real parts and imaginary parts, which are these. And if these equations are true, then the function is going to be differentiable. This f function is going to be differentiable at the point. Okay, and if f is differentiable, then its derivative is going to be the partial of x plus I times the partial with respect v with respect to x. It's just going to be that. Okay, or you could just like replace the x with a vy here, vy minus I uy, just because that's equal to that, and vx is equal to negative uy, okay? So those are the Cauchy-Riemann equations, and that's their importance. Now, do you guys remember what holomorphic means? So holomorphic. What's the difference between holomorphic and differentiable? Okay, holomorphic means
order differentiable
it's
for all the
different.
points on the disk.
Yes. In a neighborhood or a disk of Z0. So it's holomorphic at Z0 if it's differentiable in a neighborhood of Z0, not just right at Z0 or not just like on or whatever, but where you can actually draw a disk around Z0 and it's differentiable everywhere inside that disk. So that's holomorphic. Okay, now, if these are true, then if you take this first one right here, and you take another partial with respect to x, then you're going to get this. Okay, and if you take another partial of this with respect to y, you're going to get this. And so if you add, so that's they're doing the calculations right here. Now, if you add these together, you add those together, and you add these together, well, these are just, okay, if the function is continuous and stuff, and you just have a few conditions, which like every single function that you've seen satisfies these conditions, you can reverse the order of taking the partials and it'd be the same. So that means that this is going to be 0 over here. And a function that satisfies this is called harmonic. And also, you could also, it also turns out if you could do the same kind of argument, and then you get Vxx plus Vyy is also equal to 0. Okay, so if the Koshirimo equations hold, then your function is going to be harmonic. So if the function is holomorphic, then the real parts and imaginary parts are both going to be harmonic functions. Okay, so if f is holomorphic, then u and v are harmonic. Okay, so they're real functions in 2 variables right here. So if f is holomorphic, or differentiable in a neighborhood of the z0, then u is going to be harmonic and v is also going to be harmonic. And then you can also say they are harmonic, or the proper way would be just to say V is the harmonic conjugate of U. So V is the harmonic conjugate of U. Okay, so that's how you would say it. Okay, so let me, it also turns out that if you have a harmonic function, then you can use that harmonic function to construct a holomorphic function. So let me give you a quick example of that. Okay, so we'll say U is 2x cubed minus 6xy squared. Okay, so let's make sure that this is harmonic first. So this is a real valued function. What's the partial of U with respect to x? Anybody?
Squared, 6x squared minus 6y squared.
Exactly. Okay, now what's the second partial of U with respect to x?
12x.
Good, that's 12x. Okay, now what's the partial of U with respect to y?
Negative 12x.
Negative 12xy, right?
Y.
And what's the second partial of U with respect to y?
Negative 12x.
Okay, and then if you take uxx plus uyy, then you're going to get 12x minus 12. You're going to get 0, right? Okay, so U is harmonic. Okay, so if you have a function that's harmonic, it turns out that there exists a holomorphic function where this U here is the real part of that holomorphic function, and then V is then whatever V is going to be the imaginary part. Okay, so let me show you. So let's do this. Let's find a u. I mean, let's find out a u. Let's find v such that f equals this with this u here, 2x cubed minus 6xy squared plus iv is holomorphic. Okay, so let's go ahead and do that. Does that sound exciting? Or like solving a mystery, which is like most of mathematics. So where should we start? Any ideas? What is the condition for being, that we just talked about? What's the condition for being holomorphic? For a function to be holomorphic, what's the condition that we just talked about?
It has to be differentiable in a neighborhood.
Yes. Yes. And, but what is the way that we what I'm trying to get at is the Koshirimo equations here. Okay. We want it to satisfy that, okay?
Yeah.
So
we have to do the partial derivative.
Yes. So first of all, we're gonna say ux has to be equal to vy, right?
Yeah.
So what is ux? So here's u. What's the partial of u with respect to x? Yeah, we already calculated it here.
6x squared, yeah. Minus 6y squared.
Okay, and that has to be the partial of v with respect to y, right? Okay, so partial of v with respect to y has to be 6x squared minus 6y squared. Okay, can you think of a function v whose partial is this? Whose partial with respect to y is this? How do we get this term, 6x squared? Ignore this one for now. Right? How do we get this? What expression, when I take the partial with respect to y, will this give me this?
6x squared y.
Yes, 6x squared y, right? And then what expression, when I take the partial with respect to y, will give me this?
It's gonna be 2y cubed.
Yes, 2y cubed. Okay, because when I take the partial with respect to y, I get the 3 coming down. I get 6y squared right there. Now also, I could have a function just entirely in x's, and if I take the partial with respect to y, that's just going to be 0. Okay, so I could potentially have that. Okay, now the other one was uy is negative vx, right? Or it's going to be vx would be negative uy. Okay, so what's the partial with respect to y of this? Oh, it's right here. It's negative 12xy, right? Okay, so that means vx has got to be 12xy. Okay. So what kind of function, when I take the partial with respect to x, I'm going to get this?
Six x squared y.
Yeah, 6x squared y, right? Okay. And then I could potentially have a function in y, because if I'm taking a partial with respect to x, then this will be 0. And so the partial of all this with respect to x is still just going to give me this. Okay, now, based on this information, and this is important. You want V to be that, and you want to be that. You want to come up with a V that is that will be this and be this also, and not the sum of these two. You don't want to add these together. It has to be this and it has to be that. This V has to equal that. This V has to also equal this. And so this x squared y, this appears in both spots. Okay, so that's going to appear once right there. That's it, just that by itself. This term appears only over here, right? This minus 2y cubed only appears there. Okay, but you're going to have that term. And it's actually this term here. It's actually this. And this is disguised. It's really a minus 2y cubed, this guy right here. And that's it. You could add a constant on the end. This term's not needed because there's no extra thing over here. So this right here will do it. And in the end, f of z equals, the u part was this one, 2x cubed minus 6xy squared, plus, and then the v part, the I part, the imaginary part was 6x squared y minus 2y cubed. Okay, and so that function there is holomorphic. It's actually what we call entire, right? Entire means it's holomorphic everywhere, because these Koshirimo equations hold everywhere. So it's holomorphic everywhere. Okay, so if you have a harmonic function, you can use that harmonic function to construct a holomorphic function. If u is not harmonic, then you can't. It's not going to be the real part of a holomorphic function. Okay, great. So let's let me see here. So let's move on a bit. Okay, so constant functions. That's where you just have it's equal to just like that. A constant function would be, an example of a constant function would be where you just have it's equal to some number, 3 plus 2i, for example. Okay, it's gonna have a real and imaginary part. So it's just no matter what value z you plug in, you're gonna get back the same number. And if it turns out that the derivative of a constant function is going to be 0 everywhere. And also, if the derivative is 0 everywhere, then the function is going to be a constant everywhere. Okay, so this would be like a constant. So it's going to be constant everywhere. So that's important to know, that if the derivative is 0 everywhere, then the function is going to be constant. And there are lots and lots of theorems in complex variables, complex analysis, where the antecedent, these are the conditions that you're given. It goes something like this. It'll read something like this. F is holomorphic, blah, blah, blah. And then it'll say, and some other thing. Okay, those would be the conditions. And then the conclusion is, oh, f is constant. Will be the conclusions. And the proof is typically gonna go like, we're gonna take these conditions, blah, 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 blah. Oh, that implies that the derivative is 0, which implies that f is constant. Okay? So if you're asked to prove something like this, then this is the strategy that you want to use. You want to get to something where the derivative is 0, and then if you get the derivative being 0 everywhere, then f is going to be constant. Okay, so let me show you an example. Number, let's see, number 20. Okay, so this one right here. Okay, so prove if f is holomorphic in the region and always real valued, then f is constant in G. Okay, and then it gives you a hint to how to get the derivative being 0. So remember that you want to prove that the derivative is 0, and then that proves it's a constant. Okay. So, and then the conditions are f is holomorphic in the region, and here's the other one right here. It's always real valued. Okay, so let's go for a proof right here. So here's 20. Let's see if we can do it in that space. Maybe not. Okay, so where to begin? Any ideas where to begin? Well, what's this condition here? F is always real valued. That implies that F is going to be U. So it's going to have a real part, right? If it's real valued, then what happens to the imaginary part? The imaginary part's just going to be 0. Okay? Or perhaps it's better if we write it this way. And then we say V is, V is always 0. Okay, so that's one way of writing that. Okay, now it says use the Koshirimo equation. So what's the Koshirimo equation? You guys remember the first one? You got to memorize these, by the way. What's the first Koshirimo equation?
It will be
equals
ux.
Vy.
What? Ux equals Vy, right?
Yeah.
Okay, so that means that Ux, okay, what's V? If V is 0, what's the partial of V with respect to Y?
0.
Yeah, that's going to be 0. And then the other Koshirimo equation is Uy equals
Negative Vx.
negative Vx, and that's going to be 0 also, right?
Yeah.
Or negative 0, but that's negative 0 is also 0. So that means, so Ux equals 0 and Uy equals 0. So what does that mean? That means that U is it's a constant, right? Okay, so if both partials of something are 0, if both partials are 0, then it has to be a constant function.
Okay.
Okay, and so that means that f of z is also a constant. And we're done, yay.
That's
Oh wait, we're supposed to show that f prime is 0. Oh wait, we could also show that f prime is 0. Maybe that's a better route to go. Hold on. We didn't follow the hint, darn it. Okay, so f prime of z, the formula is u x plus I u y, right?
Yeah.
And then those are both 0. Okay, so the derivative is 0 everywhere. 3 lines means it's 0 everywhere. Which implies f is constant. And we're done. So we put a little box there.
How do we know v is always 0 again?
Because it says f is real valued. Okay? And this is, v is the imaginary part. So if being real valued means that the imaginary part doesn't exist. That means there's no imaginary part.
Okay.
Okay, so that this part here implies that z is 0.
Makes sense.
Okay, let's take a look at some of these exercises from number 18. We'll do a few of these to end up the class. So it says, where are the following functions differentiable? Where are they holomorphic? Determine the derivative at points where they are differentiable. Okay, so here we have a bunch of functions. Yay. There's like a whole bunch of them here. Okay, so if we do some of them, then you'll still have, it won't take away very much of the fun that you're gonna have later. So I'll let you guys choose. Which one would you like to see? Should we do, here, I'll choose. I'll choose the first one, then I'll let you guys choose. Okay, so we're gonna do J, how's that? So let's do J. So this is, we'll do it over here. J. Okay, now I'm gonna rewrite this. So it said, well, it said 4 real Z times imaginary Z, but instead of real Z, I'm gonna put X, and I'm gonna write Y. So the real part of Z is X, and then Y is the imaginary part of Z. Okay, so I'm gonna write 4xy minus, and then it's Z conjugate squared. So Z conjugate is X minus IY. So like that. Okay. So what you have to do is you have to write it in the real plus imaginary part. This is not the imaginary part, by the way, because there's another I right there, so that messes everything up. So we still have a little bit of work to do. If you square this, you're going to get x squared minus y squared, because squaring that gives you the negatives. These negatives cancel out, but then you have I squared, which is -1, so it's going to be y minus y squared. And then this times this is minus 2iy, which minus ixy, so you have minus 2ixy right there. And now you distribute the negative I in, so it's going to give you minus I x squared and then plus I y squared, and then this minus and this minus cancels, but then you have another one, so it's 2xy minus 2xy. Okay. Oh, that's interesting. So is that what we have really? So this times this is I squared. Let me do this. So this is plus I squared, right? And then this is minus 1. So this is 4xy minus 2xy. That's going to be 2xy. And then we have I times y squared minus x squared, like that. Okay, so this right here is our real part, and this right here is our imaginary part. So what should we do at this point? What should we do at this point?
Okay, what are we looking for? What are the functions? Where are the functions?
Okay, so we're trying to determine where it's differentiable. And so that is determined by
Look for.
the Koshirimo equations, right?
Yeah.
Okay, so
Can we
the first one is that. Okay, so what is, so that you just have to calculate this. So what's ux? There's u.
Do y.
Yes, 2y. And then vy?
Y is
2y.
2y.
Oh, so they're the same. Okay, so now the next one is, the next Koshirimo equation is uy equals negative vx, right?
Yeah.
Okay, so what's uy? Uy is,
2x.
and vx would be
Minus 2x.
minus 2x, but then there's another minus here, so that makes it plus 2x. Okay. Whoa, so this is this function's entire. So it's differentiable
Entire.
and holomorphic everywhere. Or in all of the complex numbers. Okay? So it's entire. It's differentiable, which means differentiable and holomorphic everywhere in the entire, all complex numbers. Okay. So let's see. So that's J. Do you want to see another one? Let's see. What's another one that you'd like to see here that we can look at? That you want to look at?
E.
So any one of these.
E. 18E.
This one?
Yeah.
No. Okay. No, that's fine. Okay, we'll do this one then. So E. Okay, so 18E. So their function is cosine x times the hyperbolic cosine of y. Oops.
Oh my gosh.
Minus I times sine x times the hyperbolic sine of y. Okay, so now here we already have the u and the v, because those are both completely real. That's completely real. So it's only the only is this one right here. Okay. So the first Koshirimo equation, what's ux?
Ux is
Negative.
negative sine x.
negative sine x cos y, right?
Yes.
Yes.
Vy is, so the partial with respect to y of all this is,
Sin x cos y.
yeah, negative sine x cos y. Because this minus is also part of the v, by the way. The minus is also part of the v. The v is actually negative sine x sinh y. Okay, now that's the first one, and those are the same. Those are exactly the same. Yay! That's true always. Okay, so now we look at the next one, which is uy equals negative vx, and uy is
Sin y cos x. I mean,
yeah sine x sinh y, right? Right.
yeah.
So it's just the derivative of cos is positive sine h hyperbolic sine of y. Okay, and then over here, this negative will cancel that negative out, so forget that. And then the partial with respect to x would be cosine x hyperbolic sine of y. Whoa, this is the same thing. Those are the same too. So this is
Entire.
it's entire differentiable homework, all of C. Again. Well, what's the fun in that? Both of them are holomorphic and they're both entire. Okay, let's see if we can find one that's not. So which one do you want to do? That you think is not going to be. Actually, you know what? I think those are the only two that are. Those might be the only two out of this whole list that are entire functions.
How come?
They might be. Let's see who. But okay, so just tell me any other one.
How about L?
L. Okay, that's a good choice. Okay, let's do L. Oh, L. Okay, look, we have another page. Okay, so 18L. And this function is z squared minus z bar squared, which is the conjugate. And so that is going to be, what you want to do is you want to make z be x plus iy. And then that means that the conjugate is z bar is x minus iy. Like that. And then let's go ahead and expand everything out. So that's squared and that's squared. So this will be x squared minus y squared. Yeah, plus 2xy, right?
Yeah.
And then this is going to be
X squared plus.
It's also going to be minus y squared, right?
Oh yeah, minus, because it's gonna be positive and then I squared.
Yeah, so ignore that negative because the negative is right here. So I'm going to look at that. And then what's the middle term going to be?
It's gonna be negative 2xyi.
Yes. Okay, so when we distribute the negative, then
They're gonna cancel.
that's going to cancel, and so is that. And this is going to cancel that negative. So yeah, it's going to be 4.
xy.
Let's write it like this, though. Let's write. So I want to emphasize that the real part is 0, and the imaginary part is 4xyi. Okay.
Mhm.
So really u is 0, and then v is 4xy. Okay, so we take a look at the first Koshirimo equation, ux equals vy. And of course, this is going to be 0. And this is going to be what?
4x.
Excellent, good. And then we take a look at the next one, ui equals negative vx. This is going to be 0. And this is going to be
Negative 4y.
yeah, negative 4y. Okay, so if you solve this for x, then you get x. The only way this can happen is if x is 0, right? And the only way this can happen is if y is 0. So this is differentiable at 0, or 0i, which is 0. And the derivative at 0 is going to be ux plus I vx, which is going to be 0. And it's holomorphic nowhere. Okay. So not even a 0. It's not holomorphic 0 because it's only the only place that it's differentiable is 0. Not differentiable anywhere else.
So it's not holomorphic.
So it can't be holomorphic anywhere. Okay?
Yeah.
I think that answers the questions. Yeah, determine the derivatives at the points where they're differentiable, and the derivative is 0. Okay? So where are they differentiable? At 0. Where are they holomorphic? Nowhere. And the derivative where at the only place where it's differentiable is 0. Okay, do you guys want to do one more of those? One more? Maybe.
Yeah.
Let's try one of these. Let's try D. Oh, I think A is entire also, but yeah, I'll let you guys do that one. Let's try D. Okay. So 18D. So we have f of z equals e to the x, e to the negative iy. So we need to like manipulate it into a real and imaginary part. So you have this e to the iy thing, e to the negative iy actually. And so the way to handle that would be it's the cosine of negative y plus I times the sine of negative y. Okay, this is just from e to the I theta is equal to cosine theta plus I sine theta. You guys have that memorized, right? So it just comes from there. Okay, so that means that f of z is going to be, this is just going to be, cosine negative y is the same as cosine y. So this is going to be e to the x cosine y. And then sine negative y is actually negative sine y. So that's going to be minus I e to the x sine y. Okay, so that's what we get. Okay, So here's our u, and this is our v, well, with the minus. Without the I though, so with the minus. Okay, so if we have u x equals vy, what's the partial of u with respect to x?
Ex.
Cosine y.
Oh,
It's just the same thing, right? Because
Yeah.
you're only taking the derivative of this part. Well, you do have the product rule, but then that's zero. The derivative of that would be zero because that doesn't have any x's. I mean, the partial of its respect to x is just zero. So you just kind of treat that as a constant. Okay. The partial of this with respect to y.
it's gonna be cosine. What?
Yeah, that's
Ex
gonna be
cosine
negative.
y. Negative
Yeah.
x. So
Okay, so these are not equal because this is a negative. They came really close to being equal, but they have this minus here.
yeah.
But if that were a plus, then they would be been equal. But no, they're not. So, so the only way this is going to be equal is if e to the x cosine y is 0, right?
Mm-hmm.
That's the only way. And then e to the x is never 0, right? So that means that cosine y has to be 0. And that has a lot of points to satisfy that. So there's pi over 2, then there's 3 pi over 2, and then like basically pi over 2 plus any multiple of pi is going to work. Okay, we'll come back to that though. Let's go to the other one and see if that gives us more information. So uy equals negative vx. Okay, so what's uy?
It's negative x sine y.
Yes, negative e to the x sine y. Yes, yes, yes. Okay, now negative vx, that would be
It's gonna
negative
be
of this. Yes, that's going to be positive
x sine y.
e to the x sine y. Okay, so that means that, again, they're negatives of each other, so that means that's got to be 0. Okay, so e to the x sine y has to be 0. Okay, so that means that sine y has to be 0. Whoa, that's tricky. Can you think of any point, any value of y where this cosine and the sine are both 0? Is that possible? No. No, right? Because when the sine is 0, then the cosine is either 1 or negative 1.
Right.
And when the cosine, yeah, when the cosine is 0, the sine is either 1 or negative 1. So if they're all both 0, plus if they're both 0, they couldn't be able to do that really nice identity where the sum of the squares is 1. If they're both 0, then they wouldn't be able to do that. And the world would be a really bad place. So that means that nowhere
It's
differentiable. And that, of course, it's holomorphic nowhere either. It's also never holomorphic.